What's up everybody, this is Meher, and in today's lesson we are going to look at how we can start to think functionally in JavaScript. This video is part of a series where we are going to cover a lot of practical aspects of functional programming which we can apply on our day-to-day development activities at work. Before we actually go and start applying functional programming concepts to our problem statements or exercises, it makes a great deal of difference if we spend some time trying to see how programming languages have evolved over a period of time and where does functional programming even fit into the picture. So most of the early programming languages, or the first generation of languages, they made use of this keyword called as goto to transfer the control of flow. And as more and more languages were evolving and being created, and the complexity of our problem statements because of the evolution of computers and technology started to rise, we started to write even more bigger softwares, and there was a need for some ways where we could start to organize our programs in much more easier fashion. And this is the perspective we are going to start to look at functional programming in this video. So what happens few years after the usage of goto in our programming languages is that you would notice structural programming patterns came into picture. Structural programming let you organize your control flow with very basic ideas. And these ideas were, first one was sequential execution of statements. Secondly, it gave you conditional execution of your statements, which we know as if else, and later on switch case was also added. And thirdly, it was the loops, which let you iterate over particular statements X number of times. If we look at a simple problem of adding numbers in the list and we want to apply a structural programming pattern, or we want to look how structural programming pattern would apply to it, it would look something like this. So for example, if you look at the first block, what we are doing in that is we are declaring our data and we are initializing our final result with a value of 0. In the second block, what we are using is a loop, which is your iterative execution of your statements. And the final block is an if statement which checks if the output is not 0, then go ahead, return it or log it. As you can see, how structural programming pattern, these three simple patterns of loops, if statements and sequential statements, they let you organize your control flow in much more stronger way. And with the addition of functions, now you can see that a function completely changes the game. It adds much more meaning to your code base, and it creates a generic functionality and adding much more dynamicism to your code base. And these set of basic patterns which structural programming introduced made the goto statement completely obsolete, and I think there are barely any languages which we are using that use goto statements. And with the ever-growing complexity of our code bases, a new pattern seemed to emerge out of making simulations using similar language, and that was object-oriented programming. In object-oriented programming, the computational objects are not only treated as real-world objects, but they also represent the real-world objects. And some of the key elements of object-oriented programming are objects, classes, encapsulation, creating abstract data types, and even inheritance. Overall, object-oriented programming presents lots of new ideas and a way to look at your problem statement and identify entities. But the two really strong ideas in object-oriented programming, which I feel are encapsulation and inheritance. And if you look at these two ideas, which is encapsulation and inheritance, you would see that these are ways you would organize how you access the data. Now, instead of relying on imperative commands to create a program, what you would go about doing is you would identify the entities in your program. So now if we apply these two key principles of object-oriented programming to our previous problem statement where we were trying to find sum of numbers in a list, then it would look something like this. So now you could go ahead and create a class called as math, which accepts a particular list of data, and it defines some methods which you can run on that data. In the second step, now you can see that we have created an instance of that class and we are passing the same data, and now on that instance we are able to run that behavior, which is to get the sum of the numbers. In the third step, now you can see that how we are using the second key idea of object-oriented programming, which is inheritance. And what we are doing is we are extending the math class and adding a functionality of being able to manipulate vectors. So with that, now you can see how your code has completely transformed from a very structural imperative commands to a code which also contains now some behavior and contains relationship, and it has much more entities in the code base, and it's easier for us to visually create a strong mental model of how our code base is spread across different modules, or how the overall code base is structured. So now that we have seen how structural programming helps you organize your control flow and object-oriented programming helps you organize your data access, what are the key players or key entities in functional programming, and how do we start to visualize or create mental models for our problems so that we can start to apply some practical aspects of functional programming. So if we put functional programming under the lens of code organization, maintainability, and visualizing key players in our problem statement, where does functional programming fit, or what kind of key ideas functional programming is bringing to us? So one thing which functional programming cares about a lot is how do you organize your side effects. And what you mean by side effects is anything that your function does, which is anything which your function does apart from returning a value, and it could be probably manipulating the DOM, or it could be probably making an API call, or even communicating with any other system altogether, for example sending an email. So you must be wondering right now that why does functional programming even care about side effects, or why does it even want us to organize our side effects? It's for a simple reason that your softwares are getting even more complex. You have systems which are way more distributed, and they need to be orchestrated, or all these systems needs to be weaved together in a particular fashion. And the most reactive parts of your application, or which cost you the most in terms of maintenance, are the parts which cause the side effects. And functional programming identifies such reactive parts, and which it calls side effects, and it wants you to organize them in a particular fashion. So now if you look at the same program with a hint of functional programming in it, you would see that in the first block we have just declared our data. And in the second block, you would see that we have defined all these functions, and these functions are now not attached with the data as you would have seen in the object-oriented programming. So if object-oriented programming focuses more on is a relationship, your functional programming emphasizes more on computation of your expressions, values in a much more mathematical sense, which does not involve a lot of state-related changes or even having side effects. So now if we look at the third block of the code, we would notice that what we are trying to do is send some information to the database, which is in our case some of the list of numbers. And we have completely isolated this function send to database because it's obviously a side effect, because for two reasons. It depends on when you want to send it and how many times you want to send it. And along with that, you would see that we are making use of some function and also a function called as add5. And all of this is happening within the run function, which you can call it a function runner, or in our upcoming videos, we are going to refer this run function as the compose function. But for simplicity, let's consider this as a function runner, which basically runs one function after the other in the order of right to left. So along with the run function, you can also notice that there's another function called as apply functions. And now that I look at it, I realize that I shouldn't have used this function in the first place. But you can consider this as a very similar function to run, which basically runs your function, but instead of accepting a number of arguments as function, it accepts an array of functions. So now if we try to create some categorization of how we have solved this problem using functional programming, you would notice that we were completely isolating our side effect, and we have also isolated our computations, and along with that you would notice that our data is completely separate. So that's a very high level differentiation. So let's talk about the key ideas which are in functional programming. So the first key idea of functional programming is your data, and you should be able to identify data in your problem statement or in your application. For example, a simplest one would be a configuration file in your React application, where you store your site title and what navigation is going to be, or any other meta information about your application which you're storing in configuration file. And you know that that configuration file stays inert, like it does not react with your application as much as other parts of your application, and it is absolutely timeless, and you just need some sort of interpretation for your data. So the second key idea of functional programming is that it contains computations, or you should be able to identify computations from data. So calculations or computations in your program are functions that do not cause side effects. They are pure in nature, and again they also have other behaviors, like they are timeless. What I mean by timeless is that, for example, it does not matter how many times you run your computation. It's going to give you the same result if it follows the principles of pure functions. For example, you can try to recall the utility library in your application, which probably has methods like debounce, throttle, and other such functions. And you would notice that the number of bugs or the number of times you have to go to that function to change its behavior is very minimal, because it's for a simple reason that those functions or those utility functions They are not trying to manipulate state as much as the other parts of your application. So that brings us to the third key idea which we have to identify, or which we have to keep in mind when we are trying to solve a problem or analyze a problem. And that third key idea is actions. And what are actions? Actions are anything that your program or function does apart from just returning the value. So your actions are very much closely related to the side effects, but these are broad events that basically depend on when and how many times you execute them. So for example, showing a loader on the screen completely depends on when you want to show it and for how long you want to show it. And because actions are the most reactive part of your application, you would want to handle them with a lot of care. So one of the focus when we are looking at a problem statement as a functional programmer you should be keeping in mind is that you want as much of your code as possible as part of your computation or even data, and making sure that your actions are as much as isolated as possible. And that way you would be able to know that, okay, this part or this category of my code is much more prone to errors, or this is what will receive much more or many more updates depending on how the logic or how the application evolves over a period of time. But I think these three ideas are going to get much more clearer in this series, because we are going to connect these three ideas every time we are going to solve a problem and we look at a bigger picture to understand why are we doing these things in the first place. So let's look at a piece of example and try to understand this before we end this video. So this problem is pretty straightforward, and it's doing a simple job of adding a navigation item called as home to the navigation bar, which has an ID of nav. So at this moment there's nothing wrong with this program, but we would want to be able to make this program much more flexible so that it receives change in a much more friendlier way. So let's look at some of the changes that could come across our way in future. One of the change could be that you would want to change the content or formatting. Other could be that you would want to change the container element itself. And third change could be that you would probably want to change the list item itself. So to solve these three problems, what we could simply do is create a function that accepts all these dynamic parts as the parameters, and the code would look something like this. And now what we have done is we have created a function called as addNav, which accepts all these three changes as parameters. And in the function body, it's pretty much the same what was part of the original problem statement. So far, our function is able to handle some of the dynamic stuff, but what if some more changes come along the way in the future? Will it be able to handle the complexity and maintainability in the same place? So one of the changes that could come in future is that probably you would want to write to a local storage, or even probably send the information to the database back, or you would want to save it to a file. The second change probably which would come in future, or which you would definitely need, is that you would want to replace your span or direct elements with probably a list-like element, which is ul/li. And third probable change could be, for example, let's say if you want to have a different structure for your mobile navigation and a different structure for desktop altogether. And now by applying all the principles of data, computations and actions, what we can come up with is something very similar to what we have already seen with the sum function. You would want to be able to separate these three key ideas altogether. So for this program, your menu structure is the primary data source. Apart from that, you also have the ID of the element where you would want to append the menu structure. But for simplicity, let's consider that as a secondary data, and let's not treat it too differently for this simple problem. Second thing you would notice is that one of the operations we were doing was to return HTML structure that we would want to be able to add to the DOM. And in our case, instead of using string concatenation, what we have done is we have converted that into a function. So ul instead of scalar value is now a function. So ul function basically takes your menu structure and it returns back a ul/li DOM structure as an output. So all these three parts, which is add to the DOM, ul and pick data, they are now your functions, which basically take an input, return an output and pass it to the next function. So now that your ul function was able to successfully create a DOM structure, it then passes its output as an input to add to DOM function. So your add to DOM function takes two inputs. One is your container element and the second one is the DOM structure. And that's when you are finally able to add your menu structure to the navigation bar. And you would see that by doing these 3 steps, what you have achieved is you have created a simple separation of your data, computation, and side effect. And this will start to shine. For example, let's say if you would want to, instead of adding to the DOM, you want to save it to a local storage, or you print to a file, then you don't have to worry about making all the changes or state in your function. What you have to just do is you have to create a function which is saved to a local storage, plug this one out, which is add to DOM, and plug save to local storage as the function. So the biggest difference from the previous function where we were taking 3 parameter values to be able to make the same change, and this one is that in the previous example you had completely scalar values as your parameters, and in this program you have function as your parameters to this one function called as function runner, which runs one thing after the other. And by doing this, you can see that we have created a great separation of data, computation, and side effect. And because we know that your UL function is so reliable, your pick data function is so reliable, that you can write a unit test case and not be worried about it. It's only your save to DOM which depends on when you run it and how many times you run it. And that is the risky part of your application, which we have completely isolated as a side effect or as an action. And while we are actually writing a similar problem like this, you probably would not use pick data function, because I've just kept it as a representation which just takes the input and gives the same output back, just so that I can highlight that we have created a separation for data and computation. Otherwise, this function would just have 2 parts, which is UL, and the second one would be add to DOM, and your data will be passed implicitly. We can add levels of complexity to the previous example that we have done, and still we can manage to not lose the readability and maintainability of the program. For example, in this piece of code, you could see that we are able to cache to the local storage, we are able to add to the footer, we are able to add to the header, and we have introduced a new function called as add href, which basically reads your link data from your menu structure and plugs it in the DOM structure. And we are making all these active decisions while we are aware of the fact what is a computation, what is a side effect or action, and what is your data. Although this example is kind of an exaggeration of the problem statement that we were trying to solve, because you would probably not do these many things, but I was trying to get a point across that you can start to visualize or categorize this mental model of your data, your actions, and your computations. So along with being able to identify data, computations, and action, you should also start to focus or pay attention to how much you can push your code into computations, how much you can push your code into data, and keep your actions as much slimmer as possible, so that when you're dealing with change, when you're dealing with their reactive and volatile nature, you are not spending a lot of time there. So on a final note, I think functional programming brings in a lot of interesting ideas, and I think these ideas of data, computation, and your actions, I think it's just a really interesting approach to start designing your code base in such a way. Hope this content was helpful, and leave me a feedback in the comment section and let me know what else you would want me to cover. And as usual, like and subscribe and let me know.